We'll cover 1.2 section. It's about length and angles from dot products. We define dot products already in the first lecture. A dot product is dot product or inner product of a vector v, for example v1, v2, and w, for example w1, w2. It's a two-dimensional vector, and the dot product is defined as v1, w1 plus v2, w2. As I said before, the output of dot product is scalar. This is a scalar. We generalize to n-dimensional vector. So if v and w are the vectors from Rn, then v vector is v1 and so on vn with n components, and w is equal to w1, w2, and so on wn. And the inner product or dot product of v and w is equal to v1, w1 plus v2, w2 plus, and so on vn, wn. And now we consider the dot product of a v vector with itself. So a v dot product of v is equal to, by definition, v1 square plus v2 square, and so on, plus vn square. This is the norm square. Length of vector, a vector v is norm of vector. So when I write this notation, you can call the norm of vector. But if we define the dot product of vectors, the norm of vector is very easy, because it's just you calculate the dot product of itself, and then square root of, positive square root of the self dot product is the norm. So v norm of vector v is defined square root of dot product. Okay, so we can easily find the norm of the vector using a dot product. And another terminology is unit vector. We say unit vector. That means a vector. Unit vector means a vector with vector v with the norm is equal to 1. Okay, so if you find any vector, like if v vector is 1 over square root 2 and 1, 1, you can verify that this vector is a unit vector. Okay, this is called unit vector. Sometimes we say it's normalized vector. Okay, so a normalized, because normalized means that the length of the vector is right now is 1. If any vector is not a zero vector, then we can normalize this vector to a unit vector, okay, by this division. I mean, we divide with the norm of this is a norm of vector v. Okay, so we can normalize. Right now, this u vector is a unit vector because the norm of u vector is equal to 1. Okay, so this process is called this process we can say this is a normalization or a normalization. Okay, and this is an example in two-dimensional plane. There's a circle. The angle is theta, and there's a vector u. U vector is cosine theta and sine theta. And we know that the norm of u is equal to 1. So u vector is a unit vector. Okay, so u this one is a unit vector because we know that a cosine square plus a sine square is equal to 1, but a cosine square and sine square, what is that? This is u vector a norm square, okay, because this one is u dot product u, okay, so that's why. So this vector is an example of a unit vector. Now we're going to talk about perpendicular vectors. If dot product of v and w is equal to 0, then we say v and w are orthogonal or perpendicular. But I think in many cases we're going to use the word orthogonal. So I think orthogonal, that terminology is more frequently used than perpendicular. And if v and w are orthogonal, then Pythagorean theorem holds. Yeah, this we know that already. So the addition of v and w norm square is the norm square of the each vectors. The reason is that if we have v vector here and then if we have a w vector here and then they are perpendicular, and adding these two vector we get v plus w. Okay, this is called Pythagoras theorem. Okay, Pythagoras theorem or Pythagoras theorem, whatever, will be fine. we can prove that easily. So this is the question. When V and W are orthogonal, Pythagoras theorem, we're going to prove that Pythagoras theorem, okay? And as I said before, this is proof of equality, and please don't start with this equality, and you have to start just start with a complex term, okay? So the proof is start with this is complex term, okay? So we start here. And by definition, the norm square is equal to dot product of the same vector, okay? And the dot product, in the dot product, the distributive law holds. So this is V dot product, V dot V plus W dot V plus V dot W and W dot W, okay? And a dot product, well, as for complex numbers, it is not, it's not always commutative, but in a real vector, the dot product is always commutative. What I mean is that a V dot W is equal to W dot V, but only for the real vector. So if you have vectors with complex number, it should be changed. I mean, you need to conjugate the result. But anyway, if you know this, we assume that we're treating a real vector, and then we can see that this is 0 and this is 0. Okay, so by definition, V dot V is equal to V norm square, and W dot W is equal to W norm square. Well, even for a complex vector, this proof is valid. I mean, because a 0 conjugate is also 0. So even if V and W are complex vectors, and this Pythagoras theorem always hold. And okay, example 3. W vector is -1, 2. And this is an example of dot product, how to calculate dot product. Dot W is equal to 4 times -1 plus 2 times 2. So this is 0. So we can say V and W are orthogonal. So I'm going to write this way. Okay, so this symbol is used for orthogonal. Okay. This is example 4 of dot product, and V dot U is equal to 1 times cosine theta times 0 times sine theta. And so this is cosine theta. And so we have to know that in geometry, I mean, geometry. So if we have any vector where you can measure angle between u and v, and u dot v is equal to u norm times v norm times, I think it should be small. It's not a dot product, it's just multiplication of scalars and cosine theta. Okay. So this equation holds. What is theta? Theta is angle between two vectors, u and v. Okay. So in deep learning or machine learning, you can see sometimes they say we're going to use the cosine similarity, and because u vector and v vector could be embedded vector or just a feature vector or whatever. And if you learn machine learning or deep learning, you know we represent the data using a vector, and then but in many cases we want to measure the similarity or the difference. Okay, so if you want to measure the similarity, in many cases you use a cosine similarity, that is this one. Okay, so so if you calculate the dot product between u and v, what you get is similarity, because angle is equal to 0. I mean, the cosine is a decreasing function. So so if u vector, the norm of u and norm of v is equal to 1, I mean they're all unit vectors, in that case the dot product of u and v is equal to cosine theta. Because if I say the dot product stands for the similarity, but there's a bias of the magnitude. Okay, so magnitude is multiplied. I mean, so magnitude is multiplied. But if you normalized the feature vector of a cat or a dog or whatever, if you have a feature vector in I don't know whether you already learned machine learning or deep learning, but anyway, if you represent something by vector and the vector is normalized already, then the dot product show that their similarity is a cosine similarity. The angle between two vectors. If v dot w is greater than 0, then angle between v and w is less than 90 degree. Okay, and if v and w a dot product of v and w is less than 0, negative, then angle between v and w is greater than 90 degree. Okay, so if I draw a v and w this way, and you can immediately notice that dot product of v and w will be greater than 0, will be positive. But v in this direction and v vector and w vector, in this case dot product v dot w should be less than 0 because this angle is theta is greater than 90 degree. And that's why we can get this sign, negative sign. We said before that a dot product of v and w is equal to norm of v times norm of w times cosine theta. So when we take absolute value, and then we can have this absolute value is equal to absolute value of v and w norm and cosine theta. But as you know, this is all is greater than or equal to 0, and also cosine theta value, absolute value, is less than or equal to 1. And then we can see that dot product of v and w, the absolute value is less than or equal to v norm times w norm. Okay, this is the famous equality. It's called a Schwarz inequality. Sometimes it's called a Cauchy-Schwarz inequality, but in some textbook you can see that it's called a Schwarz inequality. When you see any inequality, maybe you think that that this is just inequality. That means it's not an exact thing. So maybe you think that the importance of inequality, but inequality is usually very important in any theoretical papers, any theoretical research, because if you have this kind of inequality, but if you propose any algorithm, but you prove that your algorithm satisfies the equality, or just very close to equality, that means your algorithm is almost perfect. Okay, because theoretically we have inequality, but if you find any good algorithm, and then you check the inequality, and then if the inequality is equality, for example, if it's equal to the right hand side, that means your algorithm is perfect. Okay, so it's like if we know some, and not just this inequality, in any engineering or any science, if you know some bound, or for example Cramer-Rea bound or whatever, and so if you found any bound or inequality, and then somebody proposed algorithm, and then you check that, and then it's very close to the equality, that means that algorithm is very nice. Okay, so theoretically the inequality is important. We're gonna prove the triangle inequality. This is very famous inequality, using dot product. The proof starts with this term, norm square, because usually the normal vector includes the square root. So in proof, usually we use the square of the norm, because the square of the norm is the dot product of itself. So that's why. And then so we start with this term, and then by definition we can change into dot product by definition, because the norm square is the dot product of itself. And now we apply distributive law, and v dot v plus v dot w plus v dot w plus w dot w. Okay? And by definition is a v dot v is equal to norm square of v and 2 times v dot w and w norm square. But we know that this is less than equal to, this is the same, and then, but by Short's inequality, we can change this to product of norm. You see that we change this term using Short's inequality, okay? But this is equal to v norm of v and w norm square, okay? So if we square root of both sides, we can get this inequality. I mean triangle inequality using Short's inequality. Okay, but I think you should remember this first line, because norm square. I mean a norm square is just the dot product of itself. And we consider a plane in 3 dimensions. So this plane could be represented by this, but we assume that we're going to consider only the plane. I mean through the origin. Okay, the origin. We're going to consider only this, because this is a vector space, because vector space should be closed under addition and a scalar multiplication. But if you scale any point in the plane that is not through the origin, it's not a vector space, so we will consider the plane through the origin. And then we can represent that plane using this formula. Okay, this is the set, and n vector we call this is a normal vector. The normal means, it's a normalized, means that that is a unit vector, but the normal is a 90 degree. So if we have 3 dimension, and there could be a plane through the origin, okay? But there should be a normal vector. I mean, that normal vector is orthogonal to any vector in the plane. Okay, we can continue to section number 3. Section 1.3. So 1.3, matrices and their column spaces. And we know the example of matrix. So we know some example. This one is called identity matrix. identity matrix. But this example is 3 by 3, 3 by 3, because it has 3 rows and 3 columns. And another example is 2, 0, 0, 0, 4, 0, 0, 0, 5. This kind of matrix is called diagonal matrix. Diagonal matrix, because only the diagonal elements are non-zero and the other elements are all zero. This is also 3 by 3. Okay, the size of this matrix is because it has 3 rows and 3 columns. And another terminology is if we have minus 3, 0, 4, 7, 0, 0, 5. In this case, we call this matrix as upper triangular matrix. Okay, this is upper triangular matrix because when you draw a triangle, but you should include the diagonal. But I mean, the triangle, inside the triangle, the elements could be, are non-zero, but other parts is all zero. Okay, this is all zero. So that's why we call this matrix as upper triangular matrix. They're all the size of the matrix. They are all 3 by 3, 3 by 3. We call this this is a size of matrix. Okay. How many rows how many columns do they have? We check that, and then for example, if you write this matrix like 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, what is the size of this matrix? So you can see that there are 2 rows and 5 columns. So the size of this matrix is 2 by 5. Okay. This is another example matrix, and A4 is equal to 0, 0, 1. In that case, A is minus 1, 0, 0. A1 is a column vector, and 1, minus 1, 0, 0, 1, minus 1, and 0, 0, 1. Okay, we have 3 by 4. This is the size of the matrix is 3 by 4. And if we multiply a matrix to the x vector, minus 1, 0, 0, 1, minus 1, 0, minus 1, 0, 0, 1, and the vector is x1, x2, x3, x4. I mentioned before that the size of this matrix is 3 by 4, so the vector size should be 4 by 1. Okay, otherwise we cannot define the multiplication, so the 4 should be the same. Okay, so if we multiply, I think this time is a dot product way is much better, because we dot product between minus 1, 1, 0, 0 with x1, x2, x3, x4. Okay, so this one should be minus x1 plus x2. Okay, and the second component is the dot product, this one, and this is minus x2 plus x3, and the final one is this one, and this is minus x3 plus x4. Okay, so So we can see that when we multiply the matrix A, what we have is the difference. So that's why the matrix A is called difference matrix. So we just verified that we can calculate the multiplication of a matrix and vector is just a row way. So using the row of matrix, we just calculate the dot product, and then we can write down along the column index, okay? And the final component should be this dot product, row 3 dot x vector. And this is a row way, okay? How to calculate. And we know the column way, column picture, because the author, Gilbert Strang professor, used the column picture and row picture. If you see the YouTube lecture by Professor Gilbert Strang, I think the lecture is was recorded, I think 2005, and then he says column picture or row picture. So I use that word. But in the 6th edition, the picture, the word is gone. Anyway, AX vector. We use the same difference matrix in this example. 0, 0, minus 1, 1. And x1, x2, x3, x4. Now we're going to use the column way. And as we know, this x1 meets the first column, and x2 meets the second column, and x3 meets the third column, and then x4 is the weight of the fourth column. Okay, we know that. And so minus 1, 0, 0 times x1, and 1 minus 1, 0, x2, and 0, 1 minus 1, x3, and 0, 0, 1, x4. So so this is a column way, or just a column picture of AX. And we can see that AX is, what is it? It's just AX, so we can say that AX is just a linear combination of A's columns, okay? I think this looks like D, so columns, yeah, that's right. And we can see that we are just generating a vector using the material. I mean, you have, for example, well, next page. I mean, when you learn a periodic table, for example, H2O, that means we have one oxygen molecule, oxygen atom, not molecule, but anyway, oxygen atom, and then what we have is 2 hydrogen, okay, hydrogen, I don't know, I don't know whether the spell is correct. But anyway, so we are using one atom, oxygen atom, and using two hydrogen atom. We maybe we heat something. Anyway, we have only two material, and then we made water. Okay. So this is kind of a generation of water using oxygen and hydrogen. This is so this is a concept of periodic table, and another thing is when you learn prime factorization. For example, you know that 12 is 4 times 3. But this means that 12 is composed of, we have, prime number. Prime numbers are just material like atoms in a periodic table. So what we need 2 and 3, and then how many? How many numbers are needed? And we need only 2 numbers from 2, okay? And we have just 1 of 3, okay? So with that material we can generate 12. So when you see that in the previous slide, you see that we are making a vector using the columns of matrix like this. You can feel that you have 4 generators. I mean, you have 4 columns. Using that 4 columns, you are generating a new material. I mean, you are generating new vector. So in this example, you are using how many vectors are you using? You're using the number of number of vectors for the first column is x1. Okay, so this is the weight. This is just the weight of this. This is the weight. Okay, this is also weight. So just AX is just a weighted combination. Okay, weighted linear combination of columns. So you can feel that we are using columns of A as generators of vector. Now you know that how to multiply a matrix and vectors. So, this example, when you see this equation, you need to find x1, x2, and x3. But you can immediately notice that there is no solution because we have three column vectors. But as you know, the column vectors kind of, raw material. Okay, we have raw material, and then we are generating a vector. But you see, what we want to see as a, maybe you can say it's just a cooking process. But you see, we wanna make food we wanna to make some food with the third component is should be 1. Okay, but you see that the first column vector and the second, all the column vectors has 0 here. The third component of all the vectors has 0. But what we can generate is the only vector by linear combination. By linear combination, what we can generate, the vector that has 0 as the third component, because our raw material is just 0 on on the third component. So we can immediately notice that there is no solution, because we can see that 0, 0, 0 here, but the final product, final vector has 1 in it. So we cannot generate, so if I write down all the process, 1 to 0 times x1 and 3, 4, 0 times x2 and 5, 6, 0 x3 and 2, 3, 1. Now you can see that, because the left-hand side, it doesn't matter whether x1, x2, x3. We don't know. We don't know the number, but we're pretty sure that left-hand side vector should have 0 on the third component, but the right-hand side we have 1 here, so it's impossible to find x1, x2, and x3. This is an example of a matrix that has independent columns. We have 3 columns, 1, 2, 3, 0, 4, 5, and 0, 0, 6. But we can see that the 3 columns are linearly independent, because we cannot generate a vector, any column, using other two column vectors. For example, if you want to generate, but it's very easy, because if you want to generate this vector, it's impossible, because there is no first component. The first component of other vectors, they're all 0. So you cannot make this first vector, a first column, using the other vectors. But you cannot guarantee whether for example, the question is whether the third column can be generated using first column and then second column. So what we need to do is, so I think you should learn the other definition of a linear independence, okay? And a linear dependence, other definition. Well, it's related, but the new definition of a linear dependence, or independence, whatever, because dependence is not dependent, that means independent. So the definition, a linear independence, I think independence is better. The definition of vector v1 and so on, vn, and you suppose c1 v1 and so on, cn vn is a 0 vector. Then if c1 and c2, cn should be 0, then I think it's erased. Then we can say v1 and vn, they are linearly independent. Yeah, this is the definition. I think this is a new definition. Okay, so we defined a linear independence is just the opposite of a linear dependence, and a linear dependence means that one of the vector can be generated using the other vectors. But this definition, is a little looks a little bit different, but it's a very easy to understand. For example, if Ci is not 0, what we can do is that you can send all the other vectors to the right hand side. So we can have, because we assume that this is true, okay? So this is true. And if Ci is not equal to 0, what we can do is that Ci(vi) is equal to minus C1(v1) minus and Cn(vn). You have to be careful because, I mean, Ci term is missing, okay? Is a no I here, okay? No. But Ci is not 0, so we can divide using Ci. So if we divide here, then Vi is minus Ci C1 V1 minus dot dot dot, but and so on. But as you see, no I term, okay? No I term, okay? And then Cn over Ci and Vn, okay? So now you can see that Vi, the vector Vi, is a linear combination of other vectors. That means it's dependent. So the definition says that if you assume that the linear combination of all the vectors is 0 vector, and then this is a trivial solution, okay? Because you know, if C1 and Cn is all 0, and then obviously this one holds. Obviously, it's true. So this one is a trivial solution. We say it's a trivial solution. Trivial solution. So if you assume that you can generate the 0 vector, and then there's only a trivial solution, I mean the weight should be all 0, in that case we say the vectors are linearly independent. So that is the it's rather complex definition, but you need to prove that as whether the vectors are linearly independent or not. If you want to prove that, you have to use that definition, because this definition is if you use that definition is relatively easy. Otherwise, it's the proof process is really complex, because you need to check every vector whether it could be generated as a linear combination of other vectors. Because if you have so many vectors, for example 5 vectors, and then you need to do that process 5 times. But using this definition, you can do it just, you know, just one time. Calculation is enough. And this is an example of dependent columns. You see that adding column 1 to column 2, we have column 3. So 3, 4, 3, 5, 6 is equal to 1, 1, 6 plus 2, 4, 0. So we can say this matrix A2 has dependent columns. You see that using definition, we can show that in this way: 1 times 116 plus 1 times 2, 4, 0 minus 1 times 3, 5, 6 is what is it? This is a 0 vector. Okay, and we can see that there is a non-trivial solution for this equation. I mean, the C1 V1 times C2 V2. When you consider this equation, you want to find the solution C1, C2, C3. But for independence, for linear independence, C1 we have to have only the trivial solution. C1, C2, C3 is equal to 0. But in this case, we have a non-trivial solution. Non-trivial solution is what? This is 1, 1, and minus 1. But we can generate a 0 vector here. So that's why we can say the columns of matrix A2 are dependent. This is another example with dependent columns. We can immediately notice that A3 has dependent columns, because second column 3, 6, 15 is 3 times 1, 2, 5. That's why. So we can generate the second column using the first column. As I said before, you can write down a little bit different way. I mean, if you write down this, like C1, 1, 2, 5, and C2, 3, 6, 15. We consider this equation. So we want to find the coefficient C1, C2, C3. This is 0 vector. But we found that the solution could be, we have a trivial solution always, okay? We have that solution. Trivial solution always exists. But we have another solution called C1. What is it? C1 is 3, and C2 is minus 1, and C3 could be 0. But we have a non-trivial solution. I mean, non-trivial means that one of the numbers are non-zero. But we have two non-zero, 3 and minus 1. So we found that non-trivial solution. That's why we can say the column vectors of A3 are linearly dependent. We define column space of A, the matrix A. Column space of A is defined in this way. So it's the set of all the vectors from AX. So because X is any vector in an n-dimensional space, so we have infinitely many vectors. Like so, if you multiply A, and we can have infinitely many vectors. But so we can make a set using that vectors. So the set is called column space of A. You see that in A3, the second column is just 3 times the first vector, and the third column is just 4 times the first column vector, and they're just multiple. They're just multiple of multiple of the first column vector. And what is column space of A3? What is that? Is a line. Is a line through origin in all 3. But this line should include the vector 1, 2, 5. Okay, I mean so this is the line. This is the line, but it should include the origin, 0 vector, and then should include this first vector 1, 2, 5, 1, 2, 5, and should include another vector 3, 6, 15, and it should include another vector 4, 8, 20. And this line is a column space of A3. because the column space is all the linear combinations of columns. Thinking about the column space of A, the A4 has independent columns. We can prove that easily. We just set up the equation like this: 1 0 0 0 and C2 1 1 0 0 and C3 1 1 1 0 and C4 1 1 1 1. Okay, so we just solve this equation. This is zero vector at the right hand side. We can see that this is because A4 is an upper triangular matrix. It's very easy to solve it, this equation, because when we see the last component, 1 is only here. So C4 is equal to 0. And then we see the third equation, but the C4 is already 0, but third component, a non-zero component, only available here and here, but the C4 is already 0, so C3 is equal to 0. So similarly, and then C2, when you see the second component, 0, but we have 1 1 1 here, but then C3 and C4 is already 0, and then C2 should be 0, and similarly C1 should be 0. Okay, so what we have is only the trivial solution. In that case, we have only trivial solution. That means the column vectors are linearly independent. We can easily show that. In this case, so linear combination of columns spans or generates R4. Okay, four-dimensional space, because we have 4 vectors and they're independent, so we can generate R4. So in this case, we can write with this in this way. So we can write a span of 1 0 0 0 and 1 1 0 0 and 1 1 1 0 and 1 1 1 1. So we're going to erase that. Is span of this these 4 vectors is equal to R4. So 4-dimensional space. We can write that. So in this case, we can see that if you make any equation like A4 x vector is equal to any vector b, we can say that this solution, this equation has a solution because A4 has independent columns. That means we can generate any vector. So if you put any vector b here, but we can generate anything because A4 has a, linearly independent vectors, so we can generate any vector. So if somebody puts any vector in B position, we can find the weight. I mean, we can find the solution weight in this case. For the matrix, the size is 3 by n. What is the column space of it? The candidate is the whole space. The whole space. Space R3. Could be the column space of it. we're going to consider only the 3 by 3 case for simplicity. 3 by 3. Yeah, 3 by 3 is better. Mm, 3 by 3 matrix. And the column space could be the whole space when A has 3 independent, 3 linearly independent columns. For example, if A is equal to identity matrix 1 0 0 0 1 0 0 0 1, then the column space of identity matrix is all 3. But another possibility is a plane. It's a plane in all 3 through not every plane through the origin. Okay. In that case, A has 2 independent columns. 2 independent columns. Notice that we have 3 independent columns here, and when we have a plane as a column space of matrix, we have only 2 independent columns. And the final one is a line. So line in is not the final, but anyway, all 3 through origin is a line when A has 1 independent columns. 1 independent columns. You have seen this before. I mean, if A has 1 1 1 and 2 2 2 and 3 3 3, in that case we have only 1 independent column. In this case, the column space of this matrix is just a line. But I think another possibility is just a dot, just the origin. Okay, because A could be 0 0 0 0 0 0 0 0 0. In that case, a linear combination of 3 columns is only a 0 vector, and so what we have is just a 0, just a 1 point. But well, it could be a possibility. So we have just 4 possibility in this example. I mean, a 3 by 3 A matrix. So what is the possibility of column space? There are 4 possibility. One is all 3, the whole space, and the other possibility is a plane, and the other possibility is a line, and the last possibility is just a point at the origin. Now we define rank of matrix A is number of maximum independent columns in A. Many people just omit the maximum, but I mean, if we have 4 independent columns in A, in that case, 3 columns is also independent and 2 columns are also independent. So that's why some people add the word maximum in the definition, but you have to know that. And also, we're not going to prove that right now, but columns could be rows. So if somebody says the rank of A is an independent, just the number of independent rows, it's also correct. This pound sign is the number of, okay? And no, let's just erase that. Just It's the number. When I write this is the number. Okay. So rank of A is the number of independent columns. So example, rank of this matrix, identity matrix, what is that? 0, 0, 1, because identity matrix has 3 independent columns and the rank is 3. And let me see the example. A6 is 1, 4, 2, 3, 12, 6, minus 2, minus 8, minus 4. And we have 3 columns, A1, A2, A3. The rank, what is rank? Rank of A6 is equal to 1, because we can see that this column, a multiple, if you multiply 3, then we can get the second column. And if you multiply minus 2 to the first column, then we can have the third column. So we can generate all the other vectors using the first column, and that's why the rank is just 1. And we can say that what is the column space? What is the column space of A6? It's just a line through the origin. But the line should include the vector 1, 4, 2. But you can see that also the row, the second row and third row, it can be generated using the first row. So you see the row here, and then you can see that when you multiply 4 to the row first row, you can generate the second row. So if you want to calculate the rank of the matrix, you just count the number of independent columns or number of independent rows. That is the same always. And this is the end of the lecture for the section 1.2 and section 1.3.